Okay. So last hour we have already known the plasma potential, the RF hot electrode potential, and RF ground electrode potential that changed with time, and how these curves are obtained from these scientists and from Chapman's analysis. Okay, so for the symmetrical system, the half cycle of the at least half cycle, one electrode is cathode, the other is one electrode is anode, the other one is cathode. But at half cycle, they change. So this electrode become anode, this electrode become cathode. Okay. So if you compare these curves, you will see these two electrodes behave the same in average, and this is a symmetrical system. Okay, so in symmetrical system, right? We can compare the potential, right? Here, the solid curve is the potential on the RF hot electrode, and this line is the potential on the ground electrode. Okay. And for the potential on the ground electrode, it is always equal to 0 volt. And the potential on the RF hot electrode, at least half cycle, is positively biased, positive polarity, and the other half cycle is negative polarity. So in average, the potential on the RF hot electrode is also equals to 0 volt. 0 volt. So the VT equals 0 volt for symmetrical system. Okay. And the dashed line here, is the plasma potential. And the difference between the plasma potential and the potential on the electrode surface is the sheath voltage. So the sheath voltage also change with time. This is for symmetrical system. And for a symmetric system, right? The potential on the RF hot electrode will shift toward negative biased. Okay, so the potential on the RF hot electrode in average is negative, VT negative, and this is called self-bias of the RF hot electrode. In this case, if you have a small electrode area, okay. And the potential on the ground electrode is always 0 volt, okay. So in this figure, in a symmetric system, we can plot the plasma potential again, so that the dashed line here is the plasma potential, vary with time. So at this first half cycle, the plasma potential is higher than the positive polarity on the RF hot electrode, okay, and also larger than the ground potential here. So this is the difference of the plasma potential and the potential on the RF hot electrode. This is the sheath voltage here, and here is the sheath voltage on the ground electrode, right? And in this half cycle, right, the RF hot electrode become negatively biased, and there's an offset value VT here. So the RF hot electrode is biased more negative than the amplitude of the RF output, than the amplitude of the voltage of RF output. Okay, so for example, if your output voltage is 1,000 volt from power supply. In this case, the voltage on the RF hot electrode at this half cycle might be 1,800 volt negatively, okay, minus 108,000 volt. Okay. In this case, also in this half cycle, we can see again the plasma potential is higher than the ground potential and higher than the RF hot potential. And on ground electrode, the switch voltage is very small here. But on the RF hot electrode, at this half cycle, the switch voltage become very large because the switch voltage is the difference between plasma potential and the potential on the electrode surface. Okay, so the switch voltage might be, for example, higher than 1,600 volt if your RF output voltage is 1,000 volt, plus minus. But in this half cycle, the electrode, the RF hot electrode here, will not experience a very, very high bias, negative bias. Okay, so this is a symmetrical system. So the mean plasma potential, okay, this curve, dash line here, the mean plasma potential equals to the 1/2 of the amplitude of RF, 1/2 of this amplitude, plus VT, the self-bias potential. Okay, and compare these two curves. We can see in the asymmetrical system, the switch voltage here can be much higher than the switch voltage in symmetry system. Okay, so here are the difference. So it depends on your application. If you want to run PECVD, plasma enhanced chemical vapor deposition, you might need a system more like symmetrical system. But for the RF, for the sputtering system, you need an asymmetrical system so that most potential drop exists on the RF hot electrode surface, right? Only a small electrode surface here. Okay, and in the chapter of the nature of plasma, in the chapter we have already seen the patching curve of a DC system. Okay, the patching curve was analyzed by Townsend's semi-empirical relation. Okay, so the patching curve here, the vertical axis is the breakdown voltage to start or to create a plasma. Okay, and the horizontal axis is P times D. P is the pressure of your system. D is the distance between cathode and anode. But actually the distance, the D should be the distance or the length of cathode layer thickness. Okay, D here. So in a DC system, right? In a DC glow discharge system, we have already seen this figure, the patching curve. So from the patching curve, we can see for different cases, the minimum voltage required to generate plasma will fall in different region of PD. Right? And the unit for the PD is centimeter tall. Centimeter times tall. Tall is the unit for pressure. Right? Centimeter is the unit for the distance between cathode and anode, or the cathode layer thickness. Okay, and you can give a brief look. The minimum voltage required to generate plasma fall in this region. So it's about 1 to 10 centimeter tall. Right here, 1 to 10 centimeter tall. Okay, so approximately a few centimeter tall. This is for the DC discharge. So if the PD become lower than the 1 centimeter tall, it fall into the left hand branch of the patient curve. Left hand branch of patient curve. Okay, so for this part, if the D is fixed, if the distance is fixed, this part means in a low pressure region. So in a low pressure region, if you want to generate plasma, you need higher applied voltage, so that the electrons can gain more energy within the fixed or certain distance, because the electrical field is high. If you apply higher voltage in this region, so this part is the left hand branch. Okay, and if the PD value is very large, the voltage required to generate plasma will also become larger. So it is difficult to generate plasma in this region. This part is the right-hand branch. So in the left-hand branch and in the right-hand branch, the plasma are not easy to generate. Okay, so the optimum condition happen in this region only when the P times D value is between 1 to 10 centimeter tall. 1 to 10 centimeter tall. Okay, so in the right-hand branch region, if the D is fixed, in this region it means the gas pressure is very high. So there are many collisional processes in gas phase. Many collisional processes. And electron needs to gain energy from electrical field. And when electrons travel for a longer time, right, they can gain more energy from electrical field. But if electron can only travel for a short time, and then they meet a gas atom, they will collide with gas atom and scatter to another direction. So that in this region, if the gas pressure is very high, there are too much collisional process, and the energy of electron was not high enough. Okay, so in order to let the electron gain higher energy, even though the traveling distance is short, one need to use high voltage power. Okay, so in both left-hand branch and right-hand branch, one need higher voltage to generate plasma. Okay. And in RF discharge, okay, you can also find a figure similar to the patient curve, here. So in this figure, the vertical axis again is the voltage of RF power supply, voltage of RF output. But the horizontal axis here is the pressure only, pressure P, so that the unit is tall here, right? So compare with the DC discharge, the patient curve here, right? The horizontal axis is P times D, PD. Okay, so the sheath length right, will influence the discharge behavior for DC plasma. Right? In RF discharge, okay, here. The sheath or the dark space thickness is around 1 centimeter if the pressure is kept at few millitol. For the RF discharge, the sheath is about 1 centimeter. So the sheath length does not change with pressure in this region, in this range of gas pressure. Okay, the sheath length is about 1 centimeter only. Okay, so in the RF system, RF discharge system, or the discharge behavior, look like this curve, similar to the patient curve, but the horizontal axis, the parameter is pressure only. But again, the region, there is an optimal region to generate plasma. So it means at a certain pressure region, the voltage, RF output voltage required to generate plasma can be low compared to on the left side. On the left side region, the pressure is very small. Okay, so if the pressure is too low, it's difficult to generate an RF plasma. Difficult because it requires a very high voltage. Okay. And in this place, if we look at this curve, it is about few torr, right? About a few torr of gas pressure. You might generate plasma easily. And in general, if you run PECVD system, plasma enhanced chemical vapor deposition system, the working pressure is about 0.1 millitol to 1 or 2 millitol only. It cannot be higher. Okay, so it's always a little bit close to 1 torr or less than 1 torr in PECVD system. Okay, and in sputtering system, the pressure is very low, so that the voltage required to generate plasma should be very high. Right? From this curve, from this figure, you can see that. Okay, and there are several parameters which influence the discharge behavior. So the left side here, we can see the size of the system, size of your plasma system, and electron mean free path and electron oscillation amplitude. Okay, and they all influence the discharge behavior. And for the electron mean free path, it is a factor, or it is influenced by the gas pressure. If the gas pressure is high, the mean free path is short. Okay, so it is inversely proportional to gas pressure. Okay. And the oscillation amplitude of electron coming from two sources. One is the alternative electrical field in the RF system. So the frequency of the RF system is omega here. Omega, okay. So the frequency will change, or will cause the change of the amplitude of free electron, because electron will travel back and forth by following the change of electrical field from RF system. So this amplitude here is the free electron oscillation amplitude. And the other one is also electron oscillation, but these electrons are drift electrons. Since they are gas atoms in a system, so when electrons travel, they might collide with gas atom and then change their direction of motion. Okay? And the frequency of this change is the collisional frequency. Electron random collision frequency collide with gas atom. So this frequency is the nu m. Okay, and the electron collisional frequency will influence the oscillation amplitude of drift electron. So here is the capital A, and here is a small a. All these parameters will influence the discharge behavior. Okay, so for example, in this figure, one used RF plasma with a frequency or RF output frequency of 158 megahertz, and the system for the system, the D size of the system or the distance between cathode and anode. Okay, this is a major important size of your RF plasma system. So in this case, D is much larger than these two amplitude, right? The oscillation of free electron and the drift electron. Okay, in this case, so you have a larger system, so the amplitude of the electron oscillation is smaller than your system. In this case, okay, and the electron mean free path is also much smaller than the system. Okay. So in this case, it means that the electron will not collide with your chamber wall or collide with the electrode surface easily. Okay, because the oscillation amplitude is much smaller than the distance between cathode and anode. Okay, and when you apply a RF power with the RF voltage of VT here, you can calculate the electrical field. So the electrical field equals the V divided by D. So this is electrical field. Okay, so we can find out. Here are three curves. So in upper curve, the D distance between cathode and anode is 2 centimeters, and then the middle curve is 1 centimeter, and this curve is 0.5 centimeter. Okay, and if you apply a voltage and divide the voltage by the distance, you can get electrical field. So if the distance is only 0.5 centimeter, right, the electrical field is higher than another system with a distance of 2 centimeter. Okay. So in order to generate plasma for this curve with 0.5 centimeter, it requires less or smaller voltage to generate plasma. So this is the reason. Here are three curves here. Okay, and for the left side here, at very low pressure or lower pressure region, the plasma are not easily generated. Okay, because for the low pressure system, there are less collisional process. So the electron oscillation amplitude of drift electron is large, and this electron might collide with the chamber wall and then lost to chamber wall. Okay, again in this region, and if you adjust the pressure at this certain condition, so that these two frequencies, right, oscillation of free electron and the drift electron is about the same. You can get real resonance effect, so that the electron will keep accelerating by alternating electrical field. Okay, so at this point, the voltage required to generate plasma is reduced. Okay, so this is the explanation of this figure, similar to the patching curve. And you can read more from these two papers. These two papers, very early paper, in 1950s and 1930s, right? From these two papers. Okay, and the lower figure here, shows at some condition they are to a minimum, voltage minimum. So, for example, for this curve, right, there is one minima here, and here is another minimum. So in this case, your system, right, is made of a quartz tube with 30 centimeter of the length and 2 centimeter of diameter. 2 centimeter of diameter. Okay, so so they are two dimensions, two sides. So these two sides will affect the effective oscillation. Okay. So in this, when we look at this 2 centimeter diameter here, okay. So in this case, if the amplitude of the oscillation amplitude of the drift electron, okay, when it drift back and forth like this way, right, is close to the diameter of your quartz tube, or you will see another effect. Okay, so in this case, you have a long quartz tube, right? And the electrode and the anode, they are separated by about centimeter long. This is first one, okay? But the diameter is only 2 centimeter diameter, okay? So if the oscillation amplitude of drift electron is about 2 centimeter, right? They will gain oscillation along the radial direction. So here's another oscillation, so that you can gain another minimum of the of the voltage required to generate plasma. Okay, and also for the different of the frequency. For example, this curve, the frequency of high power supply is 3 megahertz. So that you can calculate the wavelength of RF equals to 100 meter here. If you have a RF frequency of 3 megahertz, the wavelength is 100 meter. So the 100 shows the wavelength. Okay, and for the left side, the wavelength becomes smaller, right? Smaller here. It means in this part, you use RF with higher frequency, right? For example, the 50, wavelength of 15 meter here, the RF frequency is doubled, 6 megahertz, right? And here, right, the frequency is even higher. But for the low frequency RF power supply, low frequency RF power supply, you might gain the oscillation along the radial direction and get to a second minimum here. Okay. And in this class, in this chapter, we focus on capacitive type discharge. So here are examples of the capacitive system. Okay, and the first one here, is a basic diode system. So in a diode system, you place two electrodes facing each other, right? So in this case, the top electrode is connected to RF hat and through a matching network. The bottom electrode is connected to ground. So when you apply the voltage, an electrical field will be generated between the RF hat electrode and ground electrode. So you can use the electrical field to increase the energy of electron, right, by electrical force. So in this type of the system, the E field, electrical field, right, is designed to generate a plasma, right, by accelerating electrons, so that when electron has an energy high enough, they can cause electron impact ionization in the gas phase. Okay, so this is pure E type, right? E is the electrical field. Okay, and when we make an RF diode system, you can use the metallic electrode, or you can use insulating material on surface of metallic electrode. Okay, so in the case, if you place a glass or quartz plate on the surface of the RF hat electrode and on the surface of ground electrode, you can still generate plasma by RF capacitive charge. Okay. And the right figure is another type of the RF capacitive discharge. Okay, so when we look at this direction, we look at the cross section of a quartz tube. Okay, so this circle here shows the chamber wall of quartz tube. Okay, so outside the quartz tube, you can place two electrodes. So you can place a piece of metal, right, on the left side and on the right side. And these two electrodes are connected to the RF power supply through a matching network. So on left side, right, this on this side, the metallic electrode is placed outside of the quartz tube, and in the real world, the metallic electrode is contact with the quartz tube. So this part looks like the planar diode system, right? In the planar diode system is if you place a piece of quartz substrate on surface of the electrode, right? The electrode contact with the quartz, and when you apply the voltage, the surface of quartz will be charging up. Okay, and in this system, the left side of the quartz tube is contact with one electrode, the right side of the quartz tube is contact with another electrode. Okay, so when you apply an RF bias, RF power to the system, the left side, the inner wall of the quartz in the left side might charge negatively, and at the same time, the right side of the inner wall surface of the quartz might charge positively. Okay, so there will be an electrical field between the left side of the quartz tube and the right side of quartz tube. And if the electrical field is high enough, they can generate a plasma. So in this type of a system, right, when you generate plasma, the plasma will not contact with metallic electrode. So you don't need to place electrode inside your system. You can place electrode outside the system, and then through the quartz tube, and then the surface of quartz tube charge up negatively and positively, and then generate plasma. Okay, so since the electrode did not contact with the plasma, so sometimes we call this as electroless discharge. Okay. Okay, so the lower right figure, right, shows a planar type of electroless capacitive discharge. Okay, so in this case, right, the top electrode on the surface of top electrode, here is a piece of insulator. On bottom electrode, here is another piece of the insulator. Okay, so the condition is the same as the top upper right figure. Okay, so in both cases, they are named electroless capacitive discharge. Okay, and on the left side, the metallic electrode contact with plasma, so it is the RF plasma with electrode. Okay, so basically, they are this type of capacitive discharge. You can use it for your system. Okay. And here's another type of RF discharge, inductive discharge. Okay, but in our class, we will only show you a few slides of inductive source. So in the RF system, we only focus on capacitive type. Okay, because the inductive type of discharge is different from capacitive type. And sometimes if you want to do your surface treatment, right, at low pressure, it is not easy to generate plasma by inductive type. Not easy, okay? But it's easy to generate a low pressure plasma by capacitive type discharge. Okay, so we are just focused on the capacitive type discharge, not on the inductive type discharge. Okay, but anyhow, here are few examples of inductive discharge. Okay, so in the upper left figure, you can use a quartz tube, right? Quartz tube with a cylindrical shape as a chamber wall, right? So here are the chamber wall, and the quartz is insulator. So sometimes we use dielectric to name the insulator. So insulating material is dielectric material. Okay. So in this system, you can use coil to surround the wall of the quartz tube, and then apply RF power. Apply RF power. Okay. So when you apply the RF power, right, the current will flow through the coil, so that the charge, the motion of the charge particles is like a circular motion, right? So for the charge particles or charge species, when they travel in a circular direction, they will generate a magnetic field at the center, okay? So there will be a magnetic field along the axial direction, okay? So the magnetic field will cause the electrons to travel, follow a circular motion inside your system. So if there are electrons inside your system, the magnetic field will cause them to travel circularly in circular direction. Okay, and and since you also apply electrical field, right, by using the RF power, so that when the electron travel, they will get accelerated by the electrical field. Okay, so combined with the inductive H field and the RF field, you can generate plasma inside. And this type of discharge, inductive discharge, is H-type. Actually, H is the magnetic field. So there are magnetic field involved in this discharge. Okay, and the right figure, okay, also shows this type of discharge. Okay, you can use the coil to surround the quartz tube, and then generate plasma inside the quartz tube by the inductive source. Okay. So again, there must be a matching network between the RF power supply and the contact of the electrical wire here. Okay, and the lower right figure is another case of inductive type discharge. Okay, so you might see this type of the plasma in industry. So in this type of plasma, you can flow gas right from the top, and let the gas flow down and come out from bottom, and you can apply the RF power through the coil, and generate the plasma, generate the plasma inside. And usually you need a very high pressure of gas to pass through the quartz tube, so that the plasma generated belongs to thermoplasma, right? So in the chapter of the nature of plasma, we have already known, depends on the gas pressure. When you generate plasma, if the gas pressure is higher than few torr, or higher than 10 torr, the plasma behavior is thermoplasma. Okay, so the temperature of thermoplasma, might be higher than 1,000 degrees Celsius. 1,000 degrees. Okay, so the melting point of quartz, of pure quartz, is around 1,600 degrees Celsius. And if you have a piece of quartz with some impurity inside, the melting point will become lower. And if you make the quartz and so that the behavior of the quartz is more like glass. At high temperature, the glass will become soft before it melted, become soft, right? Become soft. So if you use a system and either you apply a very high, or if you apply very high pressure gas inside, and since the quartz becomes soft, right, it will distort it. So they are something you need to be aware of. In the next chapter, when we talk about the plasma generation by wave, by microwave, we will come back to see this example again. So in order to keep the chamber wall of the glass tube cool enough, you need a very, very high gas flow rate, so that you use gas to cool down the quartz tube. Okay, so there are applications in industry, but it's not included in our course. Okay, and the bottom left figure is another type of the inductive discharge. So in this case, you make a coil on top of the glass or quartz plate. On top of the glass or quartz plate, so you make coil like this way and pass through the RF power, so that the H field will generate it and then penetrate through the quartz plate. So the H field will come to the inside of the chamber. So again, the H field causes the circular motion of electron, and the electrical field accelerate electron, and then you can generate plasma inside. Okay.